You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. In this video, we will learn about the Winch object. The Winch object in OrcaFlex can be used to model length-controlled or tension-controlled winches. Winches have no mass or drag properties, and the line representing the winch wire cannot bend. If you need to capture in a model the varying properties of the winch wire itself as it is hauled in or paid out, then a more appropriate tool to use would be the line feeding function in a line object. An example of this might be a payload lowering operation in deep water where the drag imposed on the winch wire could significantly alter the payload touchdown position. The winch is represented in a model by a straight line between 2 or more connection points. These connection points are similar to the ends of a line, but there is no end A to B convention as we have in lines. As well as connecting its 2 endpoints, the winch wire may optionally pass via intermediate points, in which case it does so as if passing over a small frictionless pulley at each point. An example of this might be a crane block. The wire tension on either side of each intermediate point is then applied to that point. If the point is offset on the object involved, then this gives rise to an applied moment. Winches can be controlled by stage or by whole simulation. If controlled by stage, note the stages aren't set up here, but rather are the same stages set up on the general data form and used in other areas, such as the vessel object. Here we can see the analysis page of the general data form and the stages section, where these stages are set up. If we add an additional stage in here, and then go back to the winch data form, we can see that that new stage is now appearing here as well. Looking through the available modes now, and for the static stage, we can either specify a length or a tension. We can see the units for each mode option shown at the bottom of the data form. The units used will depend on those specified on the general data form. The dynamic stages have 4 mode options for a payout winch, and a further 3 options for a tension-controlled winch. Specified payout sets an unstretched length of winch wire to be paid out, if positive, or hauled in, if negative, at a constant rate over the duration of the stage. Specified payout rate sets a rate at which the winch wire is to be paid out or hauled in over the duration of the stage. Specified payout rate change sets a change in the payout rate, in other words, an acceleration or deceleration over the duration of the stage. Instantaneous changes in winch velocity are impossible in reality, but OrcaFlex can still model them. This type of mode can be useful for removing these jumps. Length at stage end sets a target length of the winch at the end of the stage. Specified tension sets an actual tension for the winch. Specified tension change sets the change in tension over the stage. Specified tension rate of change sets the rate of change in tension over the stage. We can input stiffness and damping properties for the winch wire, though remember that no mass properties are modelled. We can also release a winch at a certain stage, as with winch control, these stages are set on the general data form. It is possible to model the performance of the winch drive system using a detailed winch, making properties such as deadband and inertia available. By default, the simple winch type is selected. We'll build a simple model now incorporating a payout winch, before converting it to a tension-controlled winch. This is quite similar to a model we built while reviewing the link object in the previous video. The properties of the model are shown in the table. This model requires 3 objects: a vessel, a line, and of course a winch. We'll set these objects up using the data in the table. The vessel is placed at the global origin. All other properties can be left at their default settings. Line stays at the default length of 100 meters, but with 2 meter segmentation. At end A, it is connected to the vessel at a position of 35, 0, -7. And at end B, it remains fixed at 85, 0, -20. The winch remains fixed at connection 1 at 65, 0, -5, with connection 2 connected to the line at an arc length of 32 meters. The final changes we need to make to the winch are to set the stage control data. We require 4 stages plus statics as per the data in the table, yet our data form only has 2 stages. Remember that the stages on the winch data form are carried over from the general data form, so we need to go there now before completing the data here. On the analysis page of the general data form, we will introduce 2 more stages, and then adjust the durations of each stage. They are 8, 10, 5, and 10 seconds. Returning to the winch data form, as this is initially a payout winch, we can leave the modes as they are. The winch is a specified length in statics of 35 meters. Then in stage 0, the build-up stage, we have a payout of 0 meters. Stage 1 has a payout of -10, the negative value meaning it will haul in a length of 10 meters. Stage 2 is 0, so again nothing changes for this stage. Finally, stage 3 is a positive 10 meter payout, meaning the winch will pay out 10 meters. We can now run this model and watch what happens to the winch as a replay is run. Before we go on, I want to save the simulation file as payout.sim. To help review the simulation, we will look at several winch results, time histories for length, tension, and velocity. On the result form, we'll select time history, the winch object, and whole simulation. Now, because we know we need multiple results, we can hold the control key while selecting the variables tension, length, and velocity. Then, when we press show, we are presented with 3 separate time history graphs alongside the 3D view. As you may know from a previous video, we can save a combination of 3D views and results for future use by using a workspace file. This is important to do at this stage because I would like to make a change to this model and come back to the same results later. Once you have the workspace ready, in the Workspace menu, select Save Workspace and give it a name. This can be any name, and you can save multiple workspaces for one file. Remember that this is a payout winch, so the length is the controlled result. It starts at 35 meters, then hauls in by 10 meters to 25 meters, then pays out again by 10 meters back to 35 meters. Contrast this to the other two results, velocity and tension. The data we set requires the length to change by 10 meters over 10 seconds. Consequently, the winch velocity is automatically set to -1 meter per second for haul-in and 1 meter per second for payout. The tension, on the other hand, is constantly adjusting on account of the vessel responding to passing waves, in order to maintain the required payout control. At this point, it is worth noting that there are a number of spikes in the tension time history. These correspond to the step changes in velocity, and are a good reminder of the transients that can be caused by step changes like this. We will now convert the model into a tension-controlled winch and look at the same results to see what has changed. Note that when the model is reset, the results windows stay open. We can choose to leave these here, but because we saved the workspace file earlier, we can just close them and open the workspace file when we need the results again. This model needs to simulate a constant tension winch, and we're effectively saying that the length and velocity must continually change throughout the simulation in order to maintain that constant tension. On the winch data form, we now need to change the control modes for all stages, including statics. We will set a specified tension in statics of 25 kilonewtons. Then we will copy this data down in order to duplicate it for all stages. This utilises the Ctrl-D shortcut. We'll run Dynamics again and save this as a new simulation file called tension.sim. As I mentioned, we can review the same results as with the payout winch model by opening the workspace file we saved earlier. As this is tension control, it is the tension that is now the controlled result, and, unsurprisingly, having set a constant tension of 25 kilonewtons, the tension result is a flat line at 25. The velocity and length plots are continually changing in response to the passing waves in order to maintain that 25 kilonewton tension. We'll move on now to make a change to a model built in a previous video on shapes and contact, and introduce a winch in order to simulate a cable pull-in scenario. This model included a vessel and some elastic solid shapes to represent a deck and chute, as well as a line representing a cable. If you don't have this model, it can be rebuilt using the data shown in the table. If you need to do this, please pause the video now. This is the model I previously created with the data in the table. In order to help convergence, the spline starting shape needs to be used with the following spline control points. Additionally, it is necessary to use the magnitude of standard error and magnitude of standard change line statics convergence control method, with a reduced magnitude of standard change of 0.01. This model should now solve statics nice and quickly. When we originally used this model, it was only for a static analysis. This time we will be looking at dynamics, but it will be a still water application. So, before I move on, I will go to the waves page of the environment data form and set the wave height to 0. The next step is to introduce a winch into the model so that we can pull the cable up onto the deck of the vessel. We'll use the data shown in the table to set up the winch. Both ends of the winch are initially connected to the vessel at positions of 50, 0, 7.04 and -30, 0, 7.04. The rather arbitrary values for Z are just taking into account the 40mm radius of the cable. Initially connecting both ends of a winch, link or line to the same object can sometimes be helpful for positioning them before adjusting their connections to suit their final configuration. We'll come back and modify these connections in a moment. The winch wire stiffness should be 100 E3. And once again, we need to change the stage data, but this must be done on the general data form. In this case, we have the correct number of stages. We just need to adjust the durations to 5 and 70 seconds. The statics mode is the default specified length, with this being set to 80 meters. Note that we can infer this by looking at the difference between the X values for the two connection points, 50 and -30. Another benefit of sometimes temporarily connecting both ends of a winch, link or line to the same object. The next step is to modify the winch connections, with connection 2 being removed from the vessel and connected to end A of the cable, therefore requiring an arc length of 0 relative to end A. This will be a cable pull-in analysis, so we need to set a negative payout rate. I'll use stage 0, the build-up stage, to accelerate from stationary to a payout rate of -2 meters per second. So this will use the specified payout rate change mode and a value of -2. Stage 1 will then continue at the same payout rate, so we'll use a specified payout rate of -2. Now, if we run dynamics, we would expect to see something happening. But the cable isn't being moved at all by the winch. Although we've connected the winch to the cable, if we look at the cable data form, we can see that end A of the cable is still fixed to the vessel, so is unable to move. The position of this end of the cable is now controlled by the winch, so I can set end A to be free. Now, if we try dynamics again, we start to see a different problem. Things seem to be moving on okay initially, but then the cable starts to push through the contact shapes. Now, the simple answer to this problem is that we forgot to release the anchored end of the line, necessary to allow the cable to be hauled in. In the line data form, we can set end B to be released at the start of stage 0, which means at the start of dynamics. Now we can see the cable being lifted onto the vessel, and the anchored end has now been released. We do have one final issue to resolve though, which we'll see in a moment. So the simulation has reported an error and has aborted. The unstretched wire length paid out has gone to 0. This cannot be modelled. So we could either make the winch longer to avoid this, or reduce the payout rate. I'll try the latter. Say -1 meter per second instead of -2. So the model has now run to completion, and we can see, if we zoom in at the top end, there is still some winch wire left, so we haven't received that error about the winch wire going down to 0 length. We can also take a look at the replay just to confirm that as well. So the top end of the cable is being pulled along the deck by the winch, and the bottom end, having been freed from the anchor, is being moved along the seabed. So that's a summary of the winch object. We'll move on in the next video to learn about seabed friction.